Hi, everyone. So this is lecture 8. And let's go back to what we were doing yesterday. We were talking about this problem where the two ships are equal length. And then when Alice's ship is moving relative to Bob, it seems contracted. And the question was, what's the reading inside her window? And we solved this problem using two approaches. One is the physical approach, where I think about a series of snapshots, and that according to Alice, Bob's windows are too close to each other so that the events are non-simultaneous. When his front window is aligned with hers versus when his back window is aligned with her back window, those events are non-simultaneous because the separation between his windows is too short in her frame. And so here we see that non-simultaneity is easily understood in terms of length contraction. And then we use Lorentz transformation, right? In this case, we have a mixed information. We know that this event, where the front windows pass each other, we know the t of that event, and we also know x prime of that event. And so we found the appropriate Lorentz transformation formula that we can use to find t prime of that event and also x of that event, position of Bob's window. We can complete the picture by looking at a whole series of special snapshots. So this is from Bob's perspective. X and t are his coordinates in time. So the columns are his ruler markings and the rows are the values of time of special snapshots. What are the special snapshots? Well, when Alice's back window is aligned with his front, then when her back window is aligned with his back window, and even earlier, I should go in the other order. When her front window is aligned with his back, then when her back window is aligned with his back, and then when her back window is aligned with his front. And to find the values of times of these rows, the t's, I just use basically distance over speed, or distance over velocity. So that's not relativity. Where the special relativity comes in is in finding the values of clock readings or values of times in Alice's frame. So for example, look at this event that says 1.78 in her window, right? So for Bob, that happens at 2.22 times 10 to the minus 7 seconds. So the numbers in units of 10 to the minus 7 seconds, or 0.222 microseconds. But what is the time analysis window? And there are two ways to do that. First, we can use length contraction to find position of Bob's window, x equals 40. And then now that we know x and t in Bob's frame, we can find t prime in Alice's frame. We can also find x prime in Alice's frame, and it better be 0. And you can check all that. Or we can also realize that that event is x prime equals 0 in Alice's frame. It's at the back of her ship. And t equals 2.22 times 10 to the minus 7 seconds in Bob's frame. And so we can find t prime. So I encourage you to try and fill in all these numbers and try to see how it works. I might make this into a homework problem. So just to practice using Lorentz transformations and thinking about what they mean. We can also step into Alice's frame. And I just want to make sure I'm sharing what I'm supposed to be sharing. We can also step into Alice's frame and see a series of these events according to her. Now, according to her, there are more number of interesting snapshots because his windows, the separation between his windows is less than separation between hers. And we see that there are more number of interesting snapshots. When his back window is aligned with her front, then his front with her front, and his back with her back, and then his front with her back. Also, of course, Bob is moving towards her back, according to her. we can find the values of t primes, the rows, again using distance over velocity, and we can also mark out the locations of these intermediate of the positions of certain intermediate events. So for example, when his front window is aligned with her front, that obviously happens at x prime equals 50, and at that instant of her time, -1 times 10 to the minus 7 seconds, his back window will be 18 meters to the right of her origin. Again, we can fill in all these numbers, and we can use Lorentz transformations to fill in the values of times in Bob's clocks, and these all agree, right? So for example, in other words, these two pictures agree, they must agree. So let's look, for example, t equals minus 2.78, sorry, t prime minus 2.78, Bob's clock in the back reads minus 2.22, so that's Bob's back is aligned with her front. So let's go back here. Bob's back is aligned with her front, so it's minus 2.22 on his and minus 2.78 on hers. Minus 2.22 on his, round it up, and minus 2.78 on hers. So these two pictures, they must agree with each other. Okay. Also, please understand that what does it mean to say that there's the Alice's clocks read 1.78? It means that when Bob peeks from his front window into her back window, as her back window passes, he will actually see her clock reading 1.78. They will both agree on what her clock reads. They will both agree on what his clocks read. But the disagreement is the values of clock reading for a particular event. In other words, this particular event, when the back windows pass, Bob says it's 2.22, Alice says it's 1.78. And when Bob peeks into her ship, he better be fast to extend his head and back out. The ship is going really fast. But he will actually say, yeah, I can see her clocks read 1.78. Okay. So according to him, each one of her clocks runs slow, and all of her clocks are asynchronized. According to her, each one of his clocks runs slow, and they are all asynchronized. And it's the combination of this, both time dilation and relativity of simultaneity, is what's needed in order to reconcile these disagreements, as we discussed last time. Okay, good. So it's a very good exercise to fill all this in, fill all these times in. So we can also analyze, we can see there's more information here. For instance, we can see that events that are simultaneous in Bob's frame, for example, event 1, when the back windows align, and event 2, when the front windows align, are not simultaneous as seen in Alice's frame, as we expect. From her perspective, the back windows align first, and then, I'm sorry, from her perspective, the front windows align first, and then the back windows align. Okay? And that's due to length contraction. Note that to say that what's simultaneous in one frame is not simultaneous in the other is the same as to say that a single instant of time in one frame, all clocks simultaneously read the same value, is not a single instant of time in another frame, and vice versa. Right? So you take your space, you plant clocks at different points in your space, you synchronize them, they all read the same value. And as another object passes, as another frame passes with its own clocks planted, you will see that all of those clocks will be asynchronized. So let's see how that works. So here is a picture of what I just said. Okay, so we can make this effective and more clear if we use Lorentz transformation to map out the values of clocks in Alice's frame at all locations given a particular instant of Bob's time, for example, t equals 0. And let me share with you the let me share with you what I'm doing here. I'm going to share the iPod, the iPhone. I mean, I'm going to share with you the iPad. So this Lorentz transformation right here, what I'm doing is I'm setting t equals 0. So that's time on my frame. Okay, all clocks in my frame read 0. And then this follows from there. This gives the value of time on a clock that's currently passing over a particular coordinate x. And you can see, okay, so that's basically what's used to give you this picture that I just shared with you. So let me go back to that picture. Hopefully you can see it. There are several things that you can see from here. Right, so t prime equals minus gamma v over c squared times x. And so what's shown here is time t prime of events that happen at various locations in the unprimed frame at t equals 0 there. So for example, at x equals 5, t equals 0, and there's some event, right, firecracker exploding. That same event happens, first of all, it takes place at a different value of x prime, minus 5 gamma, and at a different value of t prime. And notice that if this is a positive, notice that the t prime here will be negative. Clocks that are further toward the front bumper, they're set back. And clocks that are further towards the back bumper, they're advanced forward. We've already discussed that. Also, x prime equals gamma x, right? So for example, if this x right here is 5, this x here would be larger than 5. Why? Well, because the ruler seems compressed, right? So therefore, the x prime that corresponds to the location of the same event is actually larger. Okay. So jumping back to this, how does what I just said apply here? Well, note that at any instant of Bob's time, for example, 0, when all of his clocks read the same time, clocks in Alice's back window are ahead of clocks in her front window. So you can see that each clock is ahead by 1 unit, or 1 times 10 to the minus 7 seconds. And that's true for any moment of time in Bob's frame. So here, this reads 0.78, this one reads 1.78. This reads -1, this is 0. -2.78, -1.78. Okay, and that's this idea that clocks that are towards her rear bumper are advanced. We can also see time dilation here. And that's why I'm doing all these pictures. You can see lots of these effects. So time dilation. What is time dilation? Well, to see time dilation, Bob has to track any one particular Alice's clock with the help of his assistant. So for example, Alice's back window first passes by Bob's back window and then by Bob's front window. So while 0.222 microseconds pass on all of Bob's clocks, her back window clock ticks off only 0.178 microseconds. That's the usual timing of her one moving clock. Of course, on the side, I remind you that in order to do that, he had to make use of the help of his assistant. Because remember, how do we record times of events? We plant clocks everywhere. When an event happens, we read off the value on the clocks at that right there and then. And the reason we do that is to avoid the issue of time delays. If we had only one clock with one observer, right, then there's also the additional time delay. And so this, all these funny effects in special relativity, we want to remove that triviality of the time delay from those effects. In any case, as he tracks one particular of her clock, less time ticks off on that particular clock than on any of his clocks. That's the usual time dilation, and my point is you can see that here. Okay, so he concludes that any one of her clocks are running slow, while her clocks make one tick, his make more than one tick. And notice it doesn't matter which clock Bob follows, as long as he sticks to following one particular clock. Each one of Alice's clocks are running equally slow. So for example, between Bob's t equals 0 and t equals 2.22, both of her back clock, either her back clock advances by 1.78 or her front clock advances by 1.78. So if he instead tracked her front clock, again with the help of his assistant, that he would plant here, he would again conclude that while his clocks tick off 2.22, hers tick off 1.78. And we can see this from Lorentz transformation. I want to show you something. So I'm gonna again switch to my iPad. Let me use a black color. Okay. Just a second, please. Okay. Let's say we're tracking a clock that's sitting at some particular location in her frame, X prime clock. And let's, let me do this. Some point on her coordinate, in her coordinate frame. So we have T1 equals gamma V over C squared A plus T1 prime. I'm using one of the Lorentz transformations. And T2 equals gamma V over C squared A plus T2 prime. And when we subtract these, so T2 minus T1, with delta T, becomes gamma times, let me do this, T2 prime minus T1 prime, i.e. delta T equals gamma times delta T prime. Okay? And that's your time dilation effect. And you can see the location of the clock that you track doesn't matter as long as you keep tracking the same clock, the one that keeps being located at X prime equals A. Okay, so we can say that all her clocks are slowed down. Maybe another way of saying that is all her clocks have lower frequency of ticking than all of Bob's clocks, but they're all out of phase with each other, while all of Bob's clocks are in phase. Okay, so it's just another way of summarizing the situation. All of her clocks are out of phase, but they all tick at a smaller frequency than all of his clocks. But if what I just said confuses you, don't worry. I want to point your attention to one other thing. If instead of tracking any one given Alice's clock, he is just sitting at his back, sitting in a chair in the back of his ship, and observing Alice's clocks as they pass by. Okay, so now from one moment of time to another, he's not tracking one particular Alice's clock. He's observing different of her clocks pass by. And he can again note the time difference between the reading on her clocks and the reading on his clocks. And then now he will see that it's greater on her 2 clocks that passed by than on his 1 clock. So for example, we can see that when her front clock passed by his back, it read minus 0.278 microseconds, or minus 2.78, actually minus 10. And then later, when her back clock passed by his back window, it read 0 microseconds. So all the while, his clocks went from minus 0.222 microseconds to 0. And so this is not time dilation now. Well, at least it's not time dilation as seen by Bob. So again, if he's sitting at one location and observing different clocks from Alice in Alice's ship as they pass by, he will actually conclude that more time passed on those clocks than on his 1 clock. And this has to be the case because this is now Alice timing Bob's 1 clock. Here, his back window clock. And of course, she would find that his tick off less time than hers do. So there's a lot of information here. All of these effects are apparent. And so I think it's a good idea for you to, first of all, fill in these values and see how all of these effects are encoded. I will see if I will turn this into a homework problem or not. So I think that's basically what I wanted to say. The video that you're seeing is not the first take, and it's not an issue of editing. These are not the kinds of things that I can fix with editing. Anyway, I'll see you soon. Thanks.